Okay. All right. So let me move on to the problems. So yesterday we have considered this particular problem, and while discussing it, I mentioned that uh, each time we don't have to go about solving for the deflections of some of these very standard cases like a cantilever beam under tip loading or a simply supported beam. So this particular beam, the CB beam, that is uh, in the form of a simply supported beam, if you just think about it, and it has a loading, a point loading at its mid span. So these are very standard cases, and I had shown to you that in the tutorial sheet, which I also uploaded yesterday. This is our tutorial sheet. I hope everyone can see this. Uh, in the first problem, I have given a number of cases concerning the simply supported beam. And in the second problem, I have given a number of cases involving the cantilever beam. So these can be considered to be some of the very, very standard cases. And many of the problems that we encountered, not just in the problem sets as part of your training, but also in actual professional engineering practice, can often be interpreted as a combination of some of these elementary cases. Okay, so it is in this spirit that we're going to continue with some of the other problem discussions today. So this is another problem from the tutorial sheet. Statement is very straightforward that we have to determine the reaction at the support C. So what do you think we should do here? Because you see, I mean, the solution steps for these kinds of problems, they are often not very long. Unlike problems involving the combined loading, which we had done earlier, or even the shear stress problems, some of them involve, like in each of the problems, they involve a lot of calculations and things like that. These problems are not like that. They are, in terms of the actual calculations, they are relatively straightforward, shorter, but the ideas that are present behind those short, simple calculations, they are quite neat and sophisticated. Okay, so just think about it for a minute and tell me what I should do in order to find out the deflection at this, the vertical reaction to the support C. First of all, you tell me why is this kind of a problem even given here in this tutorial sheet? Because let's say we are not doing this deflection of beams chapter. Okay, you just encounter this problem on its own. Okay, so in a real life scenario, you would be facing like that. Nobody would be coming and telling you that, okay, here is the situation, this corresponds to that particular chapter. That's in the professional engineering situation. And even in an examination situation, not like this kind of an examination where every 3-4 weeks we have one test and we have a very set syllabus, very neat and clean kind of situation. I'm talking about more national level examinations like GATE or Indian Engineering Services, things like that. These things are not going to be mentioned. It's just going to be said. Okay, this question is just going to appear in front of you and you have to figure out for yourself what you have to use. So there must be a reason why this kind of a problem is given in the deflection of beams chapter, and the reason has to do with the statical indeterminacy. So can you tell me where is the statical indeterminacy appearing?
Sir, the beam, the cantilever, which has a cantilever support and also rolling support.
Right. So if we consider the beam CA by itself, that seems fine enough. Okay, this beam CA, that seems fine. It's a simply supported beam and there is some force that is being transmitted to it at its midspan. But if we consider the cantilever beam, well, what would have been a cantilever beam had there been nothing present below the point B, but now it is no longer a cantilever beam, it's something else. So this beam BD, it has been fixed to this wall at the left end at D, but at B, there is a support below it. And this kind of a support is a redundant support. Redundant means it was not necessary to introduce this support in order to maintain the stability of this structure. Even without this roller being present beneath the point B, the BD beam would have been standing on its own. Okay, if you just fix a beam to a wall, it would just remain there. Okay, it won't fall down. So this kind of a roller present below the beam, below the beam is an extra thing. Okay, so that introduces the statical indeterminacy to the whole problem. So we understand that there is some kind of statical indeterminacy going on in this problem, which means that we have to take recourse to the deformations or the deflections present within this structure, and thereby obtain the unknown reaction forces, which otherwise, through just the equations of static equilibrium, would not have been recoverable. So what do we do actually? Okay, so
Sir,
yeah.
the deflection for the beam DB at point B is same as the deflection for the beam AC at the middle point. So we get both the deflections and we get one more equation.
Yes, very good. So this is the fundamental idea behind solving this problem. Okay, so in these kinds of problems involving, I think I lost my connection. I think I lost my connection there for a second. Can you all hear me?
Yes, sir. No,
Yes, sir, we can hear you.
And this writing up is still visible?
Yes, sir.
Okay. So, as was just mentioned, for these kinds of problems involving the statical indeterminacy, we have to isolate out one condition involving the deflection, which will give us some sort of an equation to balance something out. Okay, now the thing which we identify here, and it has been stated correctly, that we don't know anything particularly about the deflection that is taking place here. Like we don't know the value a priori, we don't know the value of this thing also. But no matter what is happening, it is clear to us that the amount of deflection that this point B as part of the beam BD that will be undergoing, that is going to be equal to the amount of deflection that will be undergone by the midpoint of this beam AC. Okay, meaning to say that they don't lose contact all throughout the deformation. Yes, because they don't lose contact, how the amount by which B comes down, the same amount, this midpoint of the beam AC, that also comes down. This is the fundamental key idea. Okay, like every problem has a heart and soul which you have to attack to tackle it. This is the heart and soul of this problem. Okay, so now you tell me in terms of actual operational steps, what do I have to do in order to equate those two deflections?
Sir, in the place of a roller between DB and AC, we consider the reaction upwards on DB and the reaction downwards on AC.
Okay, so you're thinking in terms of the individual free body diagram. So let's draw that quickly. So it would be technically wrong for me to say it's a free body diagram because I am going to still retain the wall. If I had removed the wall, then it would have been a free body diagram. Nevertheless, this is some sort of a semi free body diagram. I have the force P here, and the contact between the beam BD and the AC, that contact is represented now in this separated out picture through this interaction force let's say this is some kind of a vertical, maybe V is shear force. No? So the force BV, okay, the force in the vertical direction at the point B. And similarly, the other beam, the beam AC, that will look like this. And I will retain this picture. There's going to be an equal and opposite reaction force BV on this. Now, if you look at it look at this picture in this kind of a separated out diagram, then you can immediately identify that this first one is just a case of a cantilever beam under tip loading. It just so happens that earlier we had considered only one force like this P. Now we have two forces, but doesn't matter. It is simply like P minus BV. And this one is just a simply supported beam which has a tip loading, or not tip loading, a point loading at the midspan. So we have addressed these kinds of cases earlier. So you tell me what I should write for the deflection of this. So tell me for the deflection for the beam BD.
The P minus BV into L by 2 whole cube by 3 EI.
Very good. So this is P minus BV L by 2. So this distance, this length BD is L by 2. Okay. So the formula that I'm using, I'll just show you. So if we go back to the tutorial sheet and look at these cantilever cases, you see the very first case where we have a cantilever beam under force P. And here the deflection, the Vmax, you understand that this Vmax refers to the deflection at this tip. It is very clearly stated here also. Hope you can see this thing. Okay, so this is Vmax. Okay, so this Vmax is PL cube by 3 EI. The minus sign represents that it is in the downward direction. Okay, so that is the formula that we are using. For this one, we have the case of a simply supported beam which has a concentrated force or a point force at its midspan. So let's refer to the catalog of solutions in our tutorial sheet again. So look at the very first case. This is again a simply supported beam which has a point force at its midpoint. And for that, the deflection at that point is minus PL cube by 48 EI. Okay, again the minus sign represents that the deflection is in the downward direction. So in this context, tell me what is the deflection. So this is the deflection of the beam BD at the point B, and this is the deflection of the beam AC at the point B. So what is this value? Tell me.
BVL cube by
BV
48.
L cube by 48 EI.
Yes. So there you go. All that you have to do from here is that you set del BD B is equal to del AC at B. And from this, you are going to obtain the value of BV. And once you obtain the value of BV, what can you do?
It will be BV by 2, the reaction at C, from free body diagram of AC.
Sorry?
The reaction at C will be BV by 2.
Reaction at C. Oh, you are telling me the answer.
Yes, sir.
Okay, okay. No, but what did you do for that? I mean, it's a very simple thing, but
Free body diagram of AC.
yeah, free body diagram of AC.
Sigma Fx is 0 and sigma Fy is 0.
Right. Or you can simply do a moment balance about the point A. So this is BV. This is let's say CV, this is AV, there's going to be a C horizontal also here. Okay, but what I was suggesting is that you can take the moment balance about the point A, okay, and that is going to give you directly the value of CV. That's it. Okay, so I hope this problem is clear to you. More important than the problem steps is to understand the idea, the fundamental idea that we used in solving this problem. Okay, because certainly I'm not going to repeat this problem in any of the further tests or anything, but the spirit in which I have solved this is important. Okay, let's move on. Okay, so this is the shortest statement. Determine the force in the spring. What do I do? So first of all, again, I mean, try to develop your thinking style in a step-by-step fashion. That first of all, try to identify if there is some kind of statical indeterminacy. Yes, no?
Yes, sir.
Yes, sir. There would be statical indeterminate.
Right. I mean, it's pretty straightforward because we do have a cantilevered beam without the presence of the spring. And over this cantilever beam, there is this uniformly distributed load. And now, I mean, that cantilever beam by itself would have been a nicely stable structure. Okay, but over and above that, we have given some extra support to it in the form of this spring. And this extra support makes the overall structure statically indeterminate. I would like to point out here that even though statically determinate cases, I repeat, statically determinate cases are mathematically sound, but in real practice, you will often find that the structures are made statically indeterminate. Okay, because the convenience of the mathematics that has to be done in order to solve those real life professional situations is not the big consideration when designing them. When designing them, the main consideration is the actual safety of the structure, no matter what the situation is. So in those kinds of things, in order to make them as fail-safe as possible, some extra supports are inevitably imposed on them, even though it makes them statically indeterminate. Even though mathematically, the maths may tell you that those extra supports are really extra, they're redundant. Even then, the engineers will introduce some kind of extra supports over and above what is necessary to make the structure just stable. Okay, question is, how do we solve this problem?
So if we consider that the beam AB moves down by a distance of y, the spring force will be Ky, and for the free body diagram of AB, along with the distributed load, we have a force of Ky at point B.
All right, but what is that y?
So that would be identified by deflection formula.
Right. So, so all of you, please try to think in the way that we try to think in the previous problem. So we kind of identified some kind of equality in the deflection. In the previous problem, it was the equality of the deflection of the cantilever and the simply supported parts. Here you see what is the equality in the deflections, or if something like that is going on. I mean, it's pretty straightforward. You just have to identify it in a precise fashion. What was said just now regarding the force that is being acted on by the spring on this BA is perfectly all right. There will be a force of K times the deflection of the spring on this BA over and above this uniformly distributed load. But in terms of the deflection, what we should equate? with what?
Deflection equal to compression of spring.
Deflection in the beam should be equal to the compression in the spring. Very good. Okay, that is the key idea, that the deflection in the beam BA at the point B should be equal to the compression in the spring. It's like a very straightforward, obvious thing, but you have to very clearly and precisely extract this thing and write it in the form of an equation. So how do we write it? So first of all, we separate it out, okay? Just like we have done earlier, we separate it out like this. See if it helps us. This diagram is not yet complete because I have removed this spring, and to represent its effect, I have to give this force some spring force, okay, Fs. This is the situation, and the spring itself, well, it's just like this. Okay, so earlier it was present here, this point, and now it has come here. So there is some kind of a deflection going on here also. Okay, so now do we all understand that the amount of deflection that will be undergone by this point B as part of BA, that will be equal to the deflection in the point B as part of the spring. Okay, this is the spring. So originally it was here. It was like this at this level, and now it has been compressed and it has come down this thing. So just tell me the equation which I should write. Look at this thing, the tutorial sheet. Okay, we are talking about cantilever beams. So let us look at the cantilever cases. See if this particular case is available to us. We do have a cantilever case with uniformly distributed load on it. So the deflection at the end point represented by this V max, that is given by minus WL to the power 4 divided by 8 EI. Again, the minus sign represents that the deflection is in the downward direction. Okay, so WL to the power 4, 8 EI is the magnitude. So coming back to this problem, if you just look at this blue colored uniformly distributed load, there will be a WL to the power 4 divided by 8I amount of deflection corresponding to this thing, to this uniformly distributed load. But that is not all. There is also this tip loading acting in the vertically upward direction. This is Fs. Okay, so what is the deflection due to this Fs? If I want to write this as part of the same expression. So what I'm trying to do here is that I'm trying to write down the deflection of the beam BA at the point B.
So we will subtract due to the
Yes, we will subtract. Okay, so we are considering the deflection. So when I write this delta BA at B, I mean the deflection in the downward direction. Okay, so because I mean this to be in the downward direction, the deflection due to the force Fs in the upward direction is going to be Fs L cube by 3 EI. We have already seen this. A cantilever beam under tip loading has this magnitude of deflection. It just so happens that it is now in the upward direction, so we have to minus it out. And what about the deflection of the point B as part of the spring?
Fs by K.
Fs by K. Okay. Now the question is that if we keep this thing Fs, I mean, of course we can write like this. So let's see what do we get? Fs by so we have to equate these two things. Okay, this one and this one. See if you get this thing. Let's do it quickly. It should not take more than a minute or so. Getting?
Yes, sir.
Hello?
Yes, getting.
Okay. Okay.
Yes, sir, it is getting.
All right. So from here you are obtaining the expression for this Fs. That's it. Okay. So let's move on to the next one, which is slightly more involved. Okay. So read this question. Before the uniformly distributed load is applied on the beam, so we have this beam, and the question is starting out by saying that before we have applied this kind of a load, there is a small gap of 0.2 millimeters between the beam and the post at beam. So you see here, there is a little gap between this beam and this post. So this thing is the post, okay? This one is the post. And the top part of this post that is given by this beam. So there's a small gap of 0.2 millimeters. So just take a second to realize what is being written here. 0.2 millimeters. Okay. So 1/5 of a millimeter between the beam and the post at B. The question is that we have to determine the support reactions at A, at B, and at C. And this extra information is given that the post at B has a diameter of 40 millimeters and the moment of inertia of the beam is this much. And both the beam and the post are made of steel, having this Young's modulus of 200 GPa. I think I again lost my connection for a second there. Okay, I hope I'm audible and this thing is visible.
Yes, sir.
Yes, sir.
So this is the situation, okay? So you tell me, without talking anything about equations or anything, tell me fundamentally what is going on here.
So the deflection of the beam AC at the midpoint
Yes.
is equal to the sum of 0.2 and the compression of the post at B.
All right. Okay, but what about, I mean, I've asked you now that you first start thinking about the possibility of statical indeterminacy. So as it stands, okay, as long as the gap is there, do you think this beam is statically determinate or indeterminate?
So before contact, it will
Determinate.
be statically determinate.
Before the beam has touched this post beneath it, it is very much a statically determinate case. Okay, so there could be two situations here. Okay, so it could be that you have this load of 30 kilonewton per meter, uniformly distributed load. It could very well be such that due to the application of this load, this beam deflects, and we know that the maximum deflection is going to be at the midpoint here, but this maximum deflection is such that it is less than 0.2 millimeters. Okay, if it is less than 0.2 millimeters, then you don't have to do anything else. I mean, it's just like one of those simple problems which you have been doing. Okay, so I think for these kinds of situations, see, I mean, just now, I think Saisaran was there. He said that about the equality of the deflection and everything. That's perfectly fine. But what I'm trying to say here is that you are probably getting biased a little bit by the fact that we have been doing these kinds of problems. But I'm telling you that in a professional situation, you will not be solving problems in very well-defined contexts. Okay, nobody is going to come and tell you that this is a statically determinate situation or an indeterminate situation. You have to figure things out on your own, and you have to check things that whether this is statically determinate or indeterminate or what kind of case. So please don't get biased by the fact that this problem is part of this tutorial sheet. Rather, you develop the ability to analyze a problem like it should be analyzed from the ground up. Okay, so in a systematic fashion. So first of all, as it is given, you look at the problem like it is given. Okay, without getting biased by which tutorial sheet it is coming from. So first check that if this much is the load, then how much is the deflection at the midpoint. Okay, and that can very well be done by quickly referring to this tutorial sheet here. So we look at the question number 1, where we do have this case. Okay, this is a simply supported beam subjected to this uniformly distributed load, and under this load we have this maximum deflection at the midpoint. The magnitude is 5WL to the power 4 divided by 384 EI. So my suggestion is that first of all, you check in these kinds of situations whether the magnitude of this thing is exceeding the gap height that is actually given to us. If it is exceeding, then it means that actually touching has taken place. Okay, and then you proceed as if it is a statically indeterminate case, and then whatever steps have to be taken, we will take it. Okay, so please first of all of you check whether this magnitude of 5WL to the power 4 divided by 384 EI is exceeding 0.2 millimeters or not. Check. Okay. So
Yes, sir, it is exceeding.
it is exceeding. How much is it?
Sir, it is 2.89 millimeter.
2.89 millimeters. So exceeding by a lot. So if it is indeed 2.89 millimeters, okay, so then it is surely exceeding this thing. You're sure this is 2.89 millimeters? Seems quite a large value. Anyway, the fact remains that irrespective of the actual value of this, the fact is that this is actually exceeding this gap height. Now, exceeding this gap height means that there is contact between this midpoint of the beam and this post. Now, this post is not a rigid post. Okay, its initial length is 1 meter, but there is a possibility that due to the force that is being transmitted from this applied load through the beam to this post, it is going to get compressed. So as was stated earlier, we now have to think about the equality of the displacements. And can you please state that again, Saisaran, what you said earlier?
So the displacement at the middle point of AC will be equal to the sum of 0.2 and the compression.
Will be equal to this? Yes. Okay.
Sir, but I found my statement to be biased. So based on the explanation what you have said earlier.
Okay, so I mean the statement itself is correct as it turns out. So the deflection of the beam AC at the middle point, okay, so midpoint. That is going to be some value. Now that value, whatever this thing, this has to be equated carefully with whatever is the gap height present together with the actual compression in this thing. Okay, in this post. So tell me what is this thing now? One thing we are sure that it is going to be like there is going to be a contribution from this uniformly distributed load. Had there been no contact between this thing, this would have been the deflection. But now the deflection is lesser than that. What is causing it to be to have a deflection lesser than this thing?
So now we'll consider the indeterminate case.
Yeah, of course, indeterminate case. But my question is that what is causing the deflection of the midpoint of the AC to be less than this thing? Okay, because
the reaction at point B.
Yes, this expression itself is incomplete as of now. Okay, there is going to be a reaction force from this post on this beam. Okay, so I think it would be better if I draw the diagram. Let me draw the free body diagram itself. So I'm drawing the free body diagram. So this is the vertical reaction at A. This is the horizontal reaction at A. This is the vertical reaction at C. And over and above this, there is going to be a reaction force in the vertical direction due to the contact between the beam and the post. So this is BV. And correspondingly for the post, it's going to be BV, but in the opposite direction, and there is going to be a normal reaction from the ground. So from the ground on this post. So this is the free body diagram for that. So coming back to this expression, what should be done? I have written a minus sign here because I am understanding that so I am considering this delta AC at the midpoint in the downward direction. So this is in the downward direction. Now the force BV is in the upward direction, and the deflection due to that force on this simply supported beam will be what?
Minus BVL cube by 48 EI.
Yes, BVL cube by 48 EI. So just as a quick recap, I am considering this case. Okay, this case where there is a force P at the midpoint. Now this force P is for this particular case, this is BV, but in the upward direction. That is why this is like this. So this is the situation for the this thing. But in reality, this deflection is going to be equal to how much? It is going to be equal to the gap height, the gap height. So gap height is equal to 0.2 millimeters. Plus, there is going to be some extra movement. Okay, so it is going to move down by this gap height, and then it is going to move down some extra distance due to the compression in this post. What is the compression in this post? Go back to your lessons from first year and tell me.
So the stress by Young's modulus into 1 meter.
Tell me directly in terms of the force.
So BV by pi d square by 4 into E.
So this is actually PL by AE. Okay, so PL by AE is the formula for the deflection, for the axial deflection or the axial deformation of a slender member. So here the force P is the BV. L is how much? L is 1 meter. A, you have correctly mentioned that this is pi d square by 4, where d is the diameter of the post and E is of course the Young's modulus. Okay, so this is 200 GPa. So from this equation, what are we going to obtain? We're going to obtain BV. Is it not? So you see what has been asked here. Determine the support reactions at A, B, and C. So once we find out BV, it is straightforward to come back to this diagram. Take the sigma Fx equal to 0, which is going to give us AH equal to 0, and sigma Fy equal to 0, and the moment about either point A or point C, and you will going to get AV and CV. Okay, so from here, once you find out BV, you can find out AV as well as CV. That's it.
Sir?
Yes.
Sir, we consider here the superimposition, like the deflection due to W and then due to BV, right?
Right.
Sir, then if we consider the roller joint at point C.
This one, roller support at point C.
Roller
Yes.
supported, yes,
Yeah.
sir. Sir, then the due to force BV, the beam will lift up, right? Sir, there is no deflection.
No, say that again.
Sir, there is roller support at point C, right?
Yes.
Sir, then if we consider the BV force only on the beam AC.
Yes.
Sir, then the beam will means lift, right? Lift up about A point at some angle.
So you try to think of it like this. Okay. Why is this force BV being generated? What is causing it? What is causing the force BV to get generated?
Sir, because the beam is first means
Because the beam is coming, I mean, in a layman's language, beam is coming down. Okay, beam
yes,
is
sir.
coming down and touching the post. Like if we, I mean, in the context of mechanics and mechanics of solids, we use very sophisticated language, free body diagram and whatnot. But in an usual thing, like if you want to talk to a common person, you will say like this: no, there is some force on the beam. Beam is coming down. It is touching the post. Okay, because it is touching the post, post is giving some force on it. So this force from the post on the beam, this is BV. Okay, so the source of the force BV is this actual force, this distributed force 30 kilonewton per meter. Had this force not been present, 30 kilonewton per meter, beam would not have come down. It would not have touched the post. The reaction from the post could not have been generated. Okay, so do you think that this force B is going to be having such a value that it is going to cancel out its mother? Like its mother is this 30 kilonewton per meter, right?
Yes, sir.
Okay, so try to think of it like this. The cause here is the 30 kilonewton per meter. Effect is the BV force. That effect is not going to negate the cause out. Okay, you have encountered this kind of a situation earlier in your physics +2. like there is some kind of a phenomenon which gets generated as a cause of something and tries to resist it. It is something like that, no? That BV is kind of resist. It is generated by the 30 kilonewton per meter. Okay, so it's a very interesting thing in the sense that 30 kilonewton per meter is bringing the beam down and it is generating this force BV. But this BV force is like a naughty child. Okay, it is kind of resisting its mother. But what I'm saying here is that no matter how much it does, it will never be able to negate it, because if it does so, it will kind of get cancelled out itself. But what I'm trying to connect with this concept is something which you have already studied much before in your +2. Do you remember something like this? Almost the same kind of language was used to explain this. Can anyone answer this? I'll give you a hint. It is not in the context of mechanics, but it's in the context of very much in the context of physics. Like a mother is giving rise to a child and the child is resisting its mother. But no matter what happens, that child will never be able to cancel out the
Friction.
Inertia.
I'm telling you, not in the context of mechanics, something, another chapter.
So, due to the fear of the child.
Due to the
Fear of the child.
what? I cannot hear you. Please say that louder.
So, are you asking in the context of the physics language or?
No, but absolutely physics, proper physics chapter. I'll give you 15 seconds more. Anyone?
So is it Lamb's law?
Very good. Who said this answer?
So Chetan.
Good, good, very good, Chetan. Excellent. Excellent, actually. Lenz's law, okay. So you have encountered this in the context of Lenz's law. Okay, there is a resisting phenomenon which gets generated as part of the Lenz's law, but that effect, I mean, although the effect tries to negate the cause, but it will never be strong enough to resist, I mean, completely cancel out the cause. Okay, and if you don't remember Lenz's law, just go back and revise it. It will take you 5 minutes to revise. It's a beautiful concept, and many a time in actual engineering practice, whether I mean, it doesn't necessarily be in electrostatics or electromagnetism, okay, whether in mechanics or many other things, you will see that a same kind of thing will appear. Okay, the same kind of thinking you have to employ to understand this thing. Okay, so enough fundabaji. I will discuss another problem. Just a very quick thing for you to, it's not part of the tutorial sheet. Consider another beam like this, okay? Let's say this is like this, and there is some kind of roller support here. Now, let's do this. One moment is applied at this end. You tell me, how do I find out the reaction? Not like this actually. So I want to make this statically indeterminate. Okay, like this. Tell me now, how do I find out the reaction at this end, at this right end? I'm not going to tell you anything this time. It's a straightforward thing. Tell me. Tutorial sheet is available to you. This is after all like a cantilever thing. I'll show that page to you. Cantilever page solutions. You tell me whatever you see here. Tell me what I should do. I will not say any single thing. Everything that you need to know is present on this screen now.
So that theta max equal to n naught L by E.
Please say that again. I could not hear you.
So like in one case, it's like theta max equal to n naught L into E by I, like n naught L by D into I.
Which case are you talking about? First one, second one, third one, fourth one, fifth one?
Fourth.
So here we will use first one and fourth one, no?
First one and fourth one. Yes, first one and fourth one. Okay. So that you have identified correctly, that there is a m naught here. There is also going to be a reaction force here. Okay. So if I just think about it like this, let's say this is A, this is B. So this is AH, this is AB. There's going to be some moment here in A, and there is going to be a reaction force at BV. Okay. So we have basically, we can view this thing basically as the superposition of two cases. One is a cantilever beam subjected to this m naught end moment, and another is the cantilever beam just under tip loading. Okay, so basically it's like this, that this problem we are viewing it like this. One is this, the other is this. Okay, so this plus this is going to give you this. So you have from the catalog of solutions this thing, this one, m naught L square by twice EI is the deflection. But please note that, I mean the sense of this, okay, so be a little bit careful. But anyway, this is the magnitude corresponding to the m naught. So m naught L square by twice EI. So this will be m naught L square by twice EI. And this will be how much? This will be BV L cube by 3 EI. Okay, this deflection is in the upward direction. This deflection will be in the downward direction. So you just have to equate these two to obtain the BV. Okay, so whenever you encounter these kinds of statically indeterminate situations, first try to first of all ascertain for yourself, confirm to yourself that this is indeed statically indeterminate. Okay, and then proceed towards looking at the various available cases that you have in the catalog of solutions. All right. Of course, in a very professional engineering situation, it may not be always possible to reduce a statically indeterminate case to a combination of the various cases that is present in that table. So you may actually have to go about decomposing your problem to a statically determinate problem for which you have to actually solve for it properly and then obtain the deflection corresponding to that and maybe superimpose that with something else. But as you gain more exercise, you don't even need, you won't even need me to tell you all these things. Okay, so this is the thing.
Hello, sir.
Yes.
Sir, here in place of fixed end, if we have a hinge, then we could have easily solved it without this.
Then it would not have been a statically indeterminate problem. No? Then it would have been a simply supported beam.
Yes, sir. Then only by sigma fx and.
Yeah. Then it is a statically determinate problem. So simple force balance and moment balance would have been sufficient.
Sir?
Yes.
Sir, I have a doubt in the previous system.
By the way, class is over. Okay, so you're free to leave to the next class. If you have any doubts, just hang around. Yeah, you have doubt in the previous question.
Yes, sir.
Okay, tell me.
So, like, suppose we use this same superposition principle to find the elastic curve of the this beam, then will we get the correct answer?
Please say that again. You want to find out the elastic curve of this beam.
Suppose like we have this deformation curve is with like y equal to f of x kind of curve.
I'm not hearing you.
So like we were finding that y equal to f of x kind of curve after solving that differential equation.
Yeah. So you are obtaining some kind of an expression for the deflection all along the beam. Yes.
Yes, sir.
Yeah.
So like suppose we try to find that using this principle of superposition.
Okay.
So then will we get the correct answer or not?
You will get perfectly the correct answer. Very good question. Okay, so what he's saying is this, that it is fine that we are for the sake of obtaining the deflections at certain points, we are doing all this superposition business. But what about the deflection all along the beam? Will this thing is this thing still going to be valid? By the way, it is 11 o'clock. I urge all of you to go to the next class. Only if you wish to hang around, do hang around. Okay, but class is over officially. Please go to the next class. Okay, but I'll keep on recording. You can take a look at the last couple of minutes of discussions later on. So the thing is like this, that you see the equation that we are trying to solve to obtain our deflection curve is this. Here d square dx square is equal to m, but this m is some function of x. Okay, ultimately this is some function of x. Now this is a second order equation, but this is also a linear equation. Now it is the hallmark of linear equations that if you obtain solution corresponding to a certain situation and you obtain the solution corresponding to another situation, you can always add them up. Okay, so linear equation, you can add solutions. Had this been a nonlinear equation, this adding solution business would completely not work. Okay, never ever superimpose solutions if you have the original differential equation to be nonlinear. It will never ever work. It will be completely and horrendously wrong. So this is the hallmark of linear equations. Okay, and you can actually check for yourself simply. So you take a simple equation like this, d square y dx square I lost the connection again. So you consider a simple equation like this, d square y dx square is equal to, let's say, 3. And then you consider another equation, d square y dx square is equal to, let's say, 4x. Try to find out the solution to this, try to find out the solution to this, and then try to find out the solution to this thing. You will see that the summation of these two will be equal to the solution to this. The summation of the solutions to these two will be equal to the solution to this. Okay, and it works only because there is a linear equation. Okay, need not necessarily always be a second order equation. Even if it is a third order equation, okay, or a fourth order equation, it is still going to be valid. The only requirement is that it has to be linear. That's it. In fact, this entire superposition business, it works only because it is linear. Otherwise, never ever it will work. And it's not just in the context of mechanics of solids or dynamics or anything. It's the general theory of linear differential equations. That's it.
Thank you, sir.
All right.